Welcome, everybody. I'm Jaswanth. I'll be talking about Mosaic and XLA. You might have, some of you might have attended the talk on custom kernels by Sharad yesterday. So this is kind of you can view this as an extension to that talk, where we'll be talking about some pieces of Mosaic specifically. Pallas and Mosaic were developed by GDM, and now they're being co-developed with XLA, the XLA TPU compiler team. Pallas and Mosaic were invented by Sharad and Adam, and now there is a kind of a virtual sub-team in JAX and in the JAX core team and XLA team who are co-developing both of these pieces. So just to recap, you might have already heard this in the talk yesterday. Pallas and Mosaic are DSLs and languages that provide primitives that are escape hatches for writing low-level TPU code. This is particularly useful when the semantics that you want to express are not easily expressible in the HLO offset. And they allow you to more directly write code that expresses the programmer's intent, and they allow you to get code that would be difficult for a compiler to generate. So perhaps generating efficient code for some use case perhaps requires knowledge about some knowledge about the problem that is not immediately inferable by the compiler. So, for example, maybe some knowledge of sparsity sparsity patterns in the input, or mathematical algebraic properties, things like that. A traditional compiler would be, I guess depending on what these properties are, but it's possible that a traditional compiler would be unable to infer such a thing. So, one example might be sparsity patterns, which are kind of, if you have irregular sparsity in your input, a compiler would not be able to immediately infer that unless there is a new API that you add to the HLO offset, like a sparse dot or whatever, your sparse op. Similarly, flash attention is another example where there is a non-trivial mathematical identity that is exploited to get memory efficiency, to do attention in a blockwise manner. And so this would be very difficult for a compiler to automatically infer. It also allows expressing user-defined ops that may not be general enough to kind of warrant their own HLO op. Or they might have semantics that are specific to a use case. So one example is approximate top K, where depending on the problem, you may want a different algorithm for doing the approximate top K, and with different kind of performance characteristics. So one kind of naive example is if your problem is, if you know that for your problem the K is very large always, you could just do a sort, right? Or in other cases, maybe you want to use one hot matmul in reduction, something like that. So custom kernels allow you to more directly write code for your problem as opposed to describing your problem in a very high-level operator set. They also, when you write an XLA program, the XLA compiler does a number of things for you, driven by pretty sophisticated heuristics. So, for example, things like how your HLO ops should be scheduled, where should each of the outputs of the HLO ops be placed, what should the tile sizes be, how should ops be fused together. All of these decisions are made by the XLA compiler for you, and these decisions are driven by a set of heuristics that take into account the target platform and the bit widths of the types that you're dealing with, and the operation in question, and so on. When you're writing custom kernels, you get manual control over many of these aspects. So you're in charge of selecting good performant tile sizes for your problem. You're in charge of selecting which ops get fused into your kernel, and you're in charge of figuring out how to schedule individual ops at a high level, and so on. So you're kind of trading off simplicity for more control. And so you're now in charge of making a number of these decisions that XLA would otherwise be making for you. And ideally, we want these custom kernels to integrate pretty seamlessly with the surrounding XLA context. So as I mentioned, fusions, memory placements, etc., should work fine. Yes, there's a question.
Okay, so I want to know, what if you want your Pallas kernel not to be fused with the surrounding context, but it seems like if you write this Pallas kernel, it is also going to somehow inline into the whole module later in the pipeline and get some optimizations. Is that correct?
Yeah, that's right. So I think you generally, when you write a Pallas kernel, you have the ability to fuse surrounding XLA ops into the inputs or the outputs of the Pallas kernel. But this is controllable by you. You can say that don't fuse anything into the outputs.
Okay,
Yeah.
Yeah.
All right, but you're right in the sense that the kernel itself is embedded into the overall XLA program as a custom call, as you might know.
Okay, so was it copy inline, or is just user can also control that whether we want to inline this custom call or not?
What do you mean by inline specifically?
I mean, because if you have a custom call, it's just some function call, and then that function individually is not going to be touched by or be moved together with the surrounding code. But if you inline it, the compiler might just move things around, do some aggressive optimizations, right?
Yeah, so I don't think that is possible to do, but I don't think we have the capability to prevent scheduling, to prevent this custom kernel from being moved in relation to other ops. So custom kernels ultimately boil down to a custom call op.
Yeah.
And if you define your custom call op as having side effects or things like that, then the compiler will not move it around. But if not, if it's just like any other HLO op, then the XLA compiler will just treat it as another node in the graph for the purposes of scheduling. All right, good question. Let's move on. So how does the overall stack look? So this is a very, very high level view. So you're writing, imagine a JAX program. In the normal case, without custom kernels, your program would be lower to stable HLO, and there is the XLA HLO compiler would run a number of passes on your program and produce. Some of these passes are device agnostic, some of them are device specific, and it would ultimately produce a optimized HLO graph. And this optimized HLO graph flows through to the XLA TPU backend, and there are a number of optimizations that are performed on at this level, finally producing low-level TPU IR, and then that is compiled to a TPU executable. So that's kind of the normal flow of things. If you're writing kernels, what happens is you write it using Pallas, and these are staged and lowered into Mosaic IR. We will take a brief look at what the Mosaic IR looks like. And the Mosaic IR is further optimized and lowered progressively to produce the TPU low-level IR directly. And this TPU low-level IR passes through to the XLA TPU backend. And there are a number of low-level optimizations that are done on this low-level IR, just like in the other path. And so there are instruction scheduling, simplifications, register allocation, all of these things happen. And finally, you produce the TPU executable. So as you can imagine, in the path on the right, you are bypassing the entire HLO compiler machinery. What this means is that, as I mentioned before, you will not be getting, you will not be benefiting from all the compiler optimizations that would have been done if your program were in the HLO land. So all of those fusion decisions, all of those tiling decisions that would have happened in XLA on the left side of the picture, now you're in charge of doing them if you take the path on the right. All right. Any questions? Yes.
So you also mentioned that we will still do some optimizations on the Mosaic level. Could you briefly explain what kind of optimization is still going to be performed in this level? Because we write Pallas and we want to have the full control of the hardware or whatever. I'm not sure what kind of optimization is going to break this pattern.
Yeah, that's a great question. So maybe maybe your question will be answered in this slide. So if we zoom in a little bit into what happens. So the left side is kind of the path that I showed you on the right side in the previous picture. So you have your Pallas program, which is lowered into Mosaic IR. Mosaic has its own IR, and it's also a compiler that operates on that IR. So when I say Mosaic, it's kind of overloaded between those two. But the Mosaic IR itself is a kind of a combination of several different MLIR dialects, the standard dialects like vector, arithmetic, memref, skiff, math, etc. And there are a small number of TPU dialects, which are made available to your program via libTPU. So if your program, because you're linking against libTPU, you will get these TPU dialects automatically. And then finally, the Mosaic IR is lowered, as I mentioned, to TPU low-level IR and goes to the TPU backend. If we look in a little bit, zoom in into the Mosaic box here, there are a few different passes that run. Inferring layouts it was one of the things that happens. So layouts are essentially how logical dimensions in your buffer map to physical layout in device memory. And layouts are particularly important for performance on TPUs. Choosing a good layout often means a significant bandwidth difference in how effectively you're able to use the MXU, for example. So Mosaic tries to infer layouts that are memory efficient as well as runtime efficient. So, for example, because TPUs have a certain alignment requirement, TPU memory subsystems, certain layouts may incur more padding than other layouts, because imagine your dimensions have to be padded have to be aligned to X. The size in each dimension has to be aligned to X. Depending on how you choose the physical layout, you might end up with a small amount of no padding or small amount of padding or a huge amount of padding. So Mosaic tries to balance memory efficiency and runtime efficiency in choosing these layouts. There's also the other piece, which is some of the hardware units on the TPU expect operands to be in certain layouts. And so Mosaic will make sure that these operands are laid out according to the requirements for that hardware. The third box is unrolling. As I mentioned, the operands, the values flowing through your kernel program are primarily things like memrefs and vectors. These are kind of vectors. You can imagine them as arbitrary rank, arbitrary shaped vectors. But ultimately, the TPUs have their own native hardware shapes. So the TPU's vector registers are a certain shape. The TPU's MXUs are a certain shape. And so your program has to be unrolled to operate on smaller, finer grained blocks of data that match these smaller TPU shapes, the vector register shape. So for example, if you're doing an addition operation between two vectors, this is a simple example, you want to unroll each of these vectors to match the width of the addition add hardware unit, which in this case matches the vector register shape. And so Mosaic will automatically unroll all of these operations for you. Similarly, for a matmul op, Mosaic allows you to do a vector contraction across for two arbitrarily shaped vectors as long as the contraction dimensions match and some other criteria are met. But the TPU natively supports a specific dimension of matmul, right? So Mosaic will automatically unroll your matmul to do a piecewise matmuls along your operands and accumulate them. Yes, question.
So you mentioned layout can dominate the performance of TPU, right? So my first question is, does the user have the control of the memory layout? Because I saw that in Pallas we just write tensor, we write code in tensor semantic, but it seems like I'm not sure whether the user has the control on the memref semantic or not.
Yeah, so the layouts I'm talking about, so the memref layouts are to a large degree defined by the operands to the kernel. And so XLA's layout assignment decides what a good layout for the operands to the kernel should be. However, JAX gives you, I think, knobs to control that. So JAX has layout constraints, annotations that allow you to say, oh, I want this particular layout.
And I think another thing is, I saw, there's also a unrolling pass, but when we write Pallas, we sometimes also want to, unroll it manually, do some like software pipelining. I don't know whether this unroll can be controlled by user or will it affect the overall performance or not.
Yeah, that's a good question. So you can absolutely unroll yourself. So you can write a unrolled loop in Pallas that operates on native vector register sized pieces of your data, and that's perfectly reasonable thing to do. You can do that.
And we can control the compiler not to unroll, or the compiler is smart enough just if you saw the code, it's just gonna do nothing.
Yeah, I mean, if you are already unrolling it yourself, the compiler will just say, okay, it matches the shape. It will not unroll it further. Yeah. You also have the ability to, we'll look at this in a minute, but I think you also have the ability to write non-unrolled loops if you want, right? You can express your matmul as just a for loop inside the kernel if you want. But usually people prefer to just write jnp ... inside the kernel, and that takes care of the whole thing. All right, so let's take a very brief look into the kernel language. So your kernels typically operate on input and output refs. So X-tile ref, Y-tile ref, and O-tile ref are the references to buffers that are in vmem. Vmem is the fast SRAM on TPUs. And you can read and write to these we can read from and write to these references, and these references, you can think of them as being pointers to a JAX array. There are some special constraints around reading and writing to references because, as we will see later, the kernel body is pipelined. So as you are executing one iteration of the kernel body, the pieces of data that constitute the next position for each of these references is being simultaneously transferred through memory. So there are some constraints that having to do with that, like you cannot read a value that you've written in a previous in a iteration some time ago, because that value you've written may still be in transit to HBM. But generally, you can think of it as operating on memrefs, loading and storing to memrefs. Yes, question?
Is there a difference between the Pallas load store and the dot notation?
No. So Pallas load store, you can. It's not strictly necessary. They are convenient when you have things like masks, which are difficult to express using just normal subscript indexing operators. So that's why we have Pallas load and store. But it's perfectly fine to just use normal indexing operators. It's just if you want these other knobs, you probably want to use these. Yeah, so good segue. So Pallas has a small number of APIs beyond the standard JAX.numpy APIs. This includes like the Pallas.load and Pallas.store, and some Pallas.dynamic slice, which is different, I think, in API, like kind of the signature from JAX.lax.dynamic slice and so on. But you can use a pretty large subset of JAX APIs in there. You can use JNP JNP.zeros.
Is DS the dynamics, like PL.ds is the dynamic slice?
Yeah. Yeah. Yeah, I mean, over there, you're essentially doing a dynamic slice over the ref to get the piece of the tile that you want to matmul. And as I mentioned, you can also write for loops, control structures inside your kernel. You can also write conditionals. These are lower to the kind of the analogs in the SCIF dialect, the structured control flow dialect. And ultimately, they get lower to kind of predicated regions and things like that in the kind of the low-level assembly. All right, so how do you invoke a Pallas kernel? So I want to, Pallas will be the kind of the primary way most people use Mosaic. So I'm going to kind of talk about some of these Pallas things very quickly before we go into Mosaic. The way you invoke a Pallas kernel, you essentially wrap this thing into a Pallas.Pallas call, give it the kernel. I think there's a typo here, but that's okay. The key thing I want to highlight here is the block specs. So you'll see here in specs and out specs. These describe two important pieces of information that we need to schedule the kernel. The first is the shape of each tile, the shape of the tile that each iteration of the kernel will operate on. So because in our case there are two operands, we have two in specs consisting of like two block specs, sorry. The in specs is a list of block specs. Each block spec has a shape. So in this case, for the LHS, it's a 2, however many columns shape. And for the RHS, it's a however many rows, 2 shape. So that determines the size of the tiles. So the tiles for the LHS and the RHS are shown in the pink rectangles. The other thing you need to know to schedule memory transfers is what is the mapping from a particular, let me take a step back. This kernel executes in the context of a grid. People here are probably familiar with this idea, right? You define an iteration grid, and for each coordinate in the iteration grid, there is an instance. You can view it as an instance of the kernel executing in that iteration grid, in that coordinate. We also need a mapping for when I'm executing at a particular coordinate in the grid, what are the offsets, what are the indices of the tiles that I want to operate on in that coordinate, right? So the lambda described in the inspecs provides that information. So the lambda maps a index in the coordinate grid to the index of the block that you want to read or write for the input or output. So for the LHS case, the lambda is just saying 1 I, 0. So it's just you're moving along the rows. You're moving the tiles along the rows, and there are 3 coordinates along the row dimension in the grid. So you'll have 3 tiles essentially. And similarly for the RHS, the lambda maps j to 0j, and similarly for the output. So the combination of the shape of the tile plus how do you map an iteration index into a tile index is the information that we need to be able to schedule this kernel.
How does this code map to the downstream MRI code? So like, do we have a SCF.4 loop around it, and then the inside of the code is basically we extra slice based on the index, and then we write to the output index inside of a for kind of a SDF parallel for.
Yeah. I think I'll get to that in just a second. If you could, if I don't answer your question, we can come back. Yes.
Is there some verification to make sure that the blocks in specs match the output spec?
I don't think there is a constraint that the in-specs should match the output specs.
Like in this case, it's doing a mapple, right? So the output sheet is the tile size should be 2 by 2. So whether if there's any checks to make sure that the output specs make sure that it's a 2 by 2.
I don't think there is such a thing. You talk about just the match, making sure that the out block shape is in the general case, it doesn't have to be that way. Your output can be larger because we also have padding. Your windows can essentially have some padding in the front and in the end. So it's generally not a constraint that we verify. Yeah, this is just showing a simple example where it all matches up. Are there any questions? No? Okay. Right, so I talked about scheduling the kernel. by scheduling the kernel, I mean what we want to do is to leverage memory access pipelining. XLA, by the way, already does all of this for you. When you write a dot, jnp.dot in normal JAX programs, it compiles down to a XLA dot operator, and the dot operator internally will do all of this for you. But if you're writing a custom kernel, you have to kind of describe these block specs, but the actual pipelining will still be done for you. So the way it is done is, like the top part shows generally what we want to achieve, right? We want to have some iterations of compute, and we want the HBM reads for iteration i+1 to be initiated while we are doing the compute for iteration I. This is because HBM reads have a long latency to transfer a tile from HBM to VMem. It takes many cycles, and we don't want to have that in the critical path. So we want to issue the reads before we start issue the reads for iteration i+1 before we start the compute for I. And similarly, we want to initiate the HBM writes from the previous iteration, because those also take some amount of time. We want to overlap that with the compute. So this is kind of at a high level. This is the outcome we want to achieve, and these block specs that we have defined help us to achieve that. So essentially, when we're saying like the mapping function allows the compiler, the low-level compiler, to figure out that, okay, when I'm at iteration I need to, it will evaluate this lambda, the lambda that you've given it, and figure out what are the tiles that I need to issue a fetch for, and what are the tiles that I need to evict from VMem to HBM. So the mapping function is kind of lowered and executed in each iteration of the pipelined loop to figure out what reads and writes should be kicked off before I do this compute. And the sizes of those reads and writes are essentially the shapes that you have specified here in the block specs. Yes?
Do we use block, windows, and tiles interchangeably quite often?
Yes. I think they're all kind of, tiles is a general compiler term. Block is a Pallas term. Windows is an XLA term. They're all the same.
If you're thinking about the tile or the blocks, and Pallas, should we be more thinking about them as like the windows, so that if we do unrolling, essentially creates the chunks needed to match with 128 by 8 or like, something like that.
That's right. Yeah. So if your block shapes, there is choosing the right block shape is very important for performance. You want it to be just at the point where the cost of fetching the next block matches the cost of doing compute for the current set of blocks. And this is a non-trivial problem to come up with an optimal solution for, and which is why XLA has a number of heuristics on how to compute the block sizes. Here you can use offline search strategies to kind of evaluate good block sizes and pick one. But yes, the blocks, this loop is rolled, right? This loop is not unrolled. But within each block, the compute that happens within each block can be unrolled.
Like
Or
the chunks, basically.
exactly, yeah.
It's the pipeline.
Exactly, yeah.
I guess in your example, it wouldn't be split it further, like because it was so small. I guess the window was so small.
Yeah, yeah.
Within real applications, it would be much larger.
That's right. Yeah. Yeah. You definitely don't want to have blocks that are too small. You want to
Defeats the purpose.
exactly the native hardware units have a minimum size at which they become efficient. For example, the matmul unit, and also HBM transfers have a minimum latency that you have to pay for no matter how much data you bring in. So there's the latency part, and then there's the bandwidth part for an HBM transfer. So you definitely don't want to pick blocks that are so small that you're bound by the latency part, because it's
You don't use the compute power.
exactly. All right, so if we kind of look at the analog for the previous matmul kernel in Mosaic, this is what we might generate. Note that this is not the exact auto-generated IR. This is just a handwritten IR that kind of mimics what we would have generated, just to make it more readable, right? So we have a matmul kernel that takes in the iteration indices in the LHS block shape and type. The TN, TK are the tile sizes. They're integers. They're the tile sizes along the N and the K dimensions. So let me take a step back. Just to note on nomenclature, we're doing a N by K by M matmul here. So the second operand is the RHS tile shape, and the third one is the output or accumulator tile shape. So we do a load. So the vector load up here is just from the standard MLIR vector dialect. You do a load, and then you do a select to figure out if the output is uninitialized, if you're accumulating or if you're starting a new accumulator. And then you call the vector contraction op, which does all the heavy lifting of doing the actual matmul. Once again, you would not write this. You would write Pallas. So this is just for a view into what actually happens when you write a Pallas kernel, right? You could write it, but it's much more convenient to just write it in Pallas. The indexing maps here are they're just additional metadata that the vector contraction op requires you to provide to say what happens to each of these dimensions. So for the LHS, you're saying that for iteration index ijk, you're accessing ik, and similarly for the RHS and the output. And the iterator types, we'll talk about the iterator types in a second. We're saying that the first two dimensions are parallel, and the k dimension is a reduction dimension. So a great explainer on the indexing maps and the iterator types is available in the MLIR vector dialect documentation. So there are examples that you can look at. This is just standard MLIR dialect stuff. Yes.
Just a quick question. So you use the vector dialect to represent all of the for loops in in the very beginning of the pipeline, or is some IR that is in the middle or in the dump of the pipeline?
So the way it starts out is Pallas lowers it to this vector dialect.
Directly to, from Pallas directly to this vector dialect.
Yeah.
Okay.
The for loops are not a component of the vector dialect. They are brought in with the SCIF dialect, the structure control flow dialect. But yeah, Pallas will lower control structures to analogs in the SCIF dialect.
So lower this to SCF?
Yeah. Well, this is already lowered in some sense. There's no control flow in here that I'm showing. Maybe there is here. No, there is apparently no control flow here. So there is no SCIF here. If you were to write this using control flow, for example, the select, you could write it using a SCIF SCIF if operator. But here we're just using the select operator. We also need, given that kernel, we can wrap it into XLA's pipeline emitter. XLA internally has machinery called the pipeline emitter for pipelining loops. And all of this code that has been generated so far gets mapped into the XLA's pipeline emitter machinery. Some of these attributes that I'll call out are the iteration bounds, which are kind of the analogs of the grid that I presented to you earlier at the Pallas level. So the iteration bounds are just, in this case, they're simple. They are the shape of the matmul divided by the tile shapes in the respective dimensions, tile sizes in the respective dimensions. There's also the dimension semantics. This is used because some TPUs have multiple cores on a chip, and you want to explicitly say which of these dimensions can be parallelized across two cores on a single device. And so the first two dimensions can be parallelized, and the third one is arbitrary. So the third one will not be parallelized. And we have window params, which are what to do with each window for each operand. So the mapping from iteration indices to block indices. If you recall the slide a few slides ago, we had the lambda that we were passing to map a iteration index to a block offset. This is what this is doing. The transform indices method is pretty powerful, as we will see in a couple of slides. So an example of a more complicated example for a matmul. Let's say instead of a matmul, we had a triangular matmul. If you just wrote XLA, or if you just wrote JAX, you would just do a JNP dot dot, which would treat the right-hand side as a dense matrix, right? And you would just do a normal dense matmul, which would not be super efficient. So you would like to not compute on all the zeros on the RHS, let's say. How would you actually do this? So the transform indices function that I showed you here, it's a mapping from iteration indices to block indices. So you could kind of create a transform indices function that inspected the indices and said, am I in a 0 block or in a non-zero block? And if I'm in a 0 block, don't do anything in this iteration of the kernel. If I'm in a non-zero block, then do the matmul, right? So in this way, some iterations of your pipeline loop will not do any compute and will finish faster. And the iterations that actually are dealing with non-zero LHS and non-zero RHS will do the matmul. So the transform indices is super powerful for these kinds of selecting what blocks to compute on versus what blocks to not compute on. I should also note that the small caveat, elements along the diagonal, blocks along the diagonal, I'm not showing how those are handled here, but you would have to handle those because for those blocks, some elements in the block are zeros and some blocks are not zeros. So you want to apply masking or whatnot. Or you could just waste compute there too. You could just treat the elements along blocks along the diagonal as dense, for example. And so this speed up picture is courtesy Adam and Peter Hawkins and Sreeram Vikram. They ran this experiment where they compared the performance of a kernel, this kernel, to what would happen if you just did a dense matmul. And as expected, you will get asymptotically close to the 2x theoretical speed up compared to a dense matmul. So this shows that you're able to actually save compute. A slightly more complicated matmul, block sparse matmul. So these are kind of matmuls that are, so we're talking about block sparse matmuls, but there are real applications for these, right? Like in sparse attention and things like that, where you have some quasi-irregular sparsity patterns that you want to, when you're computing attention, that you want to avoid doing compute where there are zeros. So these examples are inspired from those use cases. So you could have a arbitrarily irregular sparse RHS. If you just did a dense matmul, of course you would, your performance wouldn't change at all, right? Between the dense and the sparse version, you would just be doing dense compute, but you have the opportunity to do much better using the same transform indices machinery that I talked about. So here, instead of the transform indices, instead of mapping an iteration index to the block that you want to compute upon, it'll find the next non-zero block. So it can scan ahead in your lambda that you've given to the kernel. You can scan ahead to the next non-zero block and issue memory fetches for that block. So you can write. So you're essentially skipping over all the zeros. So this is another example of where you can kind of write arbitrarily, sophisticated, dynamic, I guess, loops that are loops where the work done in each iteration is pretty dynamic. Yes.
Is there control over whether you can kind of schedule this on a sparse core versus tensor?
There is a, yes. So there is a, so for background, TPUs starting with V5P also have a sparse core. There is a separate dialect that Pallas sparse core calls lower to. Yes, so you can do, for example, gathers on the sparse core using Pallas, but that's separate. Yeah, we're talking about primarily tensor, how it would look if you compile this to TensorFlow. Once again, picture courtesy of Adam, Peter, and Sharad. They evaluated how this kernel would do the x-axis shows the the rate of rate of zero blocks. So as the rate of zero blocks goes up, so does the speed up you would get over the dense version, which is what we want to see, right? So sparsity is another great example of a a setting where kernels will be very efficient because they allow you to skip computation in kind of arbitrarily fine-grained ways. There are also a bunch of besides the automatic, so all of this pipelining, when to schedule the DMAs, when to write out the results, all of this stuff is automatically handled for you by the Mosaic, by the low-level compiler, the TPU backend, as long as you just specify these like the transform indices function and the shapes of the blocks that you want to fetch. So besides having this happen automatically, Pallas also gives you explicit APIs to do memory transfers. So async copy, for example, it basically lowers to a copy from HBM to VMEM or VMEM to HBM or between any two memories on the chip. So you kick off a copy and then the copy proceeds in the background and you wait for the copy to finish. Similar to async copy, there's also a async remote copy, which is pretty powerful because it allows you to do the same across many chips, right? So if you imagine your kernel is executing in a SPIMD-like fashion, you could do copies across any pair of chips in the topology. So you could use this to implement collective matmols, your own collectives, reduce, scatter, and all gather, and so on. And finally, there are the weight and barrier synchronization primitives that allow you to, have barriers to allow your program on all the replicas to reach a sort of common point before proceeding further. For example, you want to do a collective. And finally, there is also other APIs like the with memory space constraint, which give the XLA compiler hints on how to constrain the input and output memory spaces. So you can say that I want these inputs to be in VMEM before the kernel starts, and XLA will respect those constraints. All right. Finally, interoperability with XLA is really important. We want, as I mentioned before, we want to fuse XLA ops into the inputs and outputs of kernels. This is the kind of the alternative to doing this is for you as the kernel writer to explicitly, for example, if you wanted to apply some activation to the outputs of your dots, you couldn't explicitly write it in the kernel, but it would be nice if you didn't have to. So we now have the ability to fuse certain things like broadcasts, I think, and element-wise operations and certain slices, I believe, into the inputs and outputs. Finally, you can also provide, as I mentioned, hints to XLA's memory assignment infrastructure. So keep in mind that the custom kernel exists in the context of a much broader, much bigger XLA program. So the typical use case is that you have identified some specific piece of your program, of your model that you want better performance on, and you've written that piece in using Pallas. The rest of the program is still XLA. So you want to make sure that the constraints for your kernel, layouts, memory spaces, and things like that are respected by the compiler when it's compiling the surrounding ops. So there is a number of hints that you can pass to the XLA compiler. We also interoperate with XLA's layout assignment, especially tiling. We want XLA to choose tilings because the kernel writer may have chosen to only make their kernel work with certain layouts and certain tilings, and so they can express that and say that, hey, XLA, please give me this tiling because that's what I've optimized my kernel for, and XLA will do that. If it's not able to do that, it'll insert a copy to kind of copy from whatever tiling it got assigned to whatever tiling the kernel expects. There's more information on tiling whenever these slides are shared. That link will take you to the XLA documentation on tiling, so please feel free to read that. There are also a number of low-level TPU generation specific optimizations in the TPU backend, and of course you get all of these for free because ultimately you are lowering to the low-level TPU IR. You can all of the scheduling, register allocation, ILP, efficiency things you will get for free. And finally, forwards and backwards compatibility. We follow JAX's backwards and forwards compatibility guarantees. This means that if you've serialized a kernel, it will work with a version of Mosaic that's up to 6 months newer than the version at the time of serialization, or up to 3 weeks older. So if you're serializing a kernel, you don't have to, you have a compatibility window between which your kernel will work. Beyond that, you have to kind of re-export. Yes?
But like I heard for stable you have 5 years guarantee for forward and backward. Why? In this case, we have much smaller support for these versions.
This whole infrastructure relies on MLIR, and MLIR does change quite a bit. So we don't want to providing a much wider compatibility window would essentially mean that we would not be able to roll out features as fast. So we have kind of taken the kind of the conservative thing and made sure we're compatible. We will guarantee whatever guarantees you get from JAX.export. But if there are use cases where you want your serialized kernels to work, for example, years with a version of Mosaic that is years newer, let us know. I have not heard of any strong use cases for that. It does involve a very high degree of burden for Mosaic developers. So we're kind of erring on the side of moving fast and adding new capabilities. I think that's the reason. There have been a lot of recent MLIR changes that have required us to think very carefully about how to make them compatible with kernels that were serialized ages ago, right? So we're kind of generally, we want to keep the compatibility window short. But if you have use cases where this is important, please reach out. And yeah, a couple of additional resources. There's the Pallas Quick Start guide, which is great. Please look at it. There are some code examples to help you get started, and there are also some pointers to how do you analyze performance for your Matplotlib kernel on a TPU, how to think about programming TPUs and so on, which are really great. And I have added a code pointer here to where the lowering actually happens from Pallas to Mosaic, which is also a great educational resource to learn more about the internals of Mosaic. And that's all I had. Any questions? Yes.
I think this was shared before. How do you profile or see the performance of your kernel? Does it show up in your XPROF, or do you debug the kernel performance?
Yeah. So there are two things. One is it does show up in XPROF, and we have added XPROF will just show these as kernels, and you can look at whatever normal telemetry you get for HLO ops in XPROF. You can get that. We also have static analysis tools. We're in the process of open sourcing these, so hopefully they'll be available to everybody outside of Google as well. We have static analysis tools that inspect the Mosaic IR as well as the low-level TPU IR and give you visualizations about unit utilization, like how much is each hardware unit being utilized over kind of the static view of the program. So not the runtime, runtime trace like XPROF and others, but kind of statically analyzed. Yeah, so there are XPROF does support it. So if you're using XPROF, you should see this. There's also additional hooks that are also mentioned in the documentation where you can add annotations to your kernel to add tracing regions. So you can analyze a particular region of interest that you want, and that'll show up in XPROF as well. So if you're not if you're specifically interested in one particular loop inside your kernel, you can add these markers, and XProf will show you additional information about what happened in that region.
Are there other types of debugging tools for, like, for example, numerical analysis and things like that?
Not so much for numerical analysis. The Pallas does have debug print, which I think uses the low-level host recorder. Yeah. So you can sprinkle pl.debug print, and you will be able to print tensors, values of vectors and other state as the program is executing. And you can log those. So that's the primary way by which people debug these things. I'm not aware of any specifically any numerics-focused debugging tools.
Okay.
Perhaps your team will
That's
will build some for us.
yeah. I was wondering, like, what are the what people desire actually. What are the things that if is missing, or, like, specifically problems that show up and we don't have like a way for solving them.
Yeah, I think the other piece is that the choice of tile sizes also impacts numerics because tile sizes define the scope of reductions. For example, if you're doing a matmul, if you choose different tile sizes will lead to different reductions, right? And so I think we need to really think carefully about how do we help users debug those kinds of issues, where a tile size suddenly changed your numerics quite significantly. I don't have a good answer for that. I don't think anybody does. I think it's kind of, we have given up on the, like, it's kind of a known thing now, and people know to expect some numerical differences. But I think additional tools for pinpointing where there are like outliers in the inputs that kind of cause this catastrophic error propagation, those kinds of things would be useful. Yeah.
So I guess in XLA, while there are different versions of TPUs have different, I guess, specs, right? So they could have different, they could make different block sizes, could be different components. Is that kind of like also taken care of by Mosaic, or is that something you also have to consider for different regions?
No, I think that problem still exists in Mosaic because, like I said, your choice of tile size essentially determines what reductions happen, right? I think the Pallas and Mosaic have a more kind of strict, I guess, policy, a strict view on numerics. So, for example, you will not get, for most operations, where if you did a BF16 operation, XLA might sometimes decide to do it in F32 precision, but Pallas and Mosaic will generally not. So you will get BF16 precision. So there are some areas in which Mosaic takes a more strict stance on numerics, whereas XLA, because of legacy, aka we don't want to break a whole bunch of models, does transparent promotion to wider types, things like that. But I think the problem of reduction order and things like that still exist, regardless of the path you choose. Yes.
How different the Pallas to Triton for GPUs? Like, is this? I mean, I'm just trying to figure out, like, this is great for GPUs. How does it differ on GPUs?
Yeah. So Pallas is actually quite, Pallas lowers to Triton as well. I think I showed this in the first slide, right? Many of the APIs that I've shown here have analogs to Triton. So, for example, pl.load translates pretty straightforwardly to tl.load, and so on. pl.dot or jnp.dot translates to pl.dot. So many of these APIs are the same. But the other APIs, for example, async copy, async remote copy, many of these are TPU specific. So I think you use the same mental programming model when writing a kernel in Pallas versus in Pallas for a TPU versus a GPU, but the knobs that you have at your disposal for squeezing more performance will be different. There's also a new project for Mosaic for GPU, which is intended to get more performance for Hopper and future architectures of GPUs. So maybe there'll be a talk on that at some point, but yeah. The Pallas, the lowering link that I have here, if you look in here, there's also a subdirectory there for lowering to Triton. So that will have all the information you need. Generally, it just lowers to the TTIR, I guess it's called, the Triton IR, instead of Mosaic IR. Any other questions? All right. Thanks, everybody. Oh, yeah, last question.
Or is there any like forum or things to ask questions? Like, is there like a Discord, right?
Not externally. Are you talking about externally or internally at Google? Externally, yeah. So I think GitHub issues are the main way. I'm not aware of a Discord for Pallas and Mosaic level questions, but the GitHub, we do monitor the GitHub issues page quite closely. And yeah, but so that's the primary way to get support or ask questions. Thanks, everybody.